Okay, x cubed squared is x to the 2 times 3. Why is that? Because x cubed would be x times x times x. You square it, you'd have x times x multiplied by x times x times x, and you'd have 6x's multiplied. Okay. Main point, you'd have 3 here and 3 here. How many do you have? 6, but that's 2 times 3. You got 2 groups of 3, you got 6. There are many ways to see this, and of course you can just quote the rule of exponents, but better if you understand it, because it's awful easy to get confused if you don't. Okay, on this one, that's just z to the 5th squared is z to the 2 times 5, and y squared is y to the 2 times 2, which equals z to the 10th, y to the 4th. This one, you're going to have x to the 2 times 3, y to the 2 times 4, divided by z to the 2 times 5, which is x to the 6th, y to the 8th, over z to the 10th. Okay, so all that is fairly straightforward. Okay, if we got the rules for exponents, and if you're not totally sure of the rules for exponents, you can still write these things out. Bunch of x's, bunch of y's, bunch of z's. Not going to be good if you got too many of them. But you know, for these numbers, it's easy to do that. Okay. Now, I'm going to make a statement over here. It doesn't equal 6, it equals x equals 6. The square root of x to the 6 is x to the 3rd. And the square root cuts all the powers in half. Just like squaring doubles the powers, square rooting cuts them back in half. So you kind of end up with what you started with. Okay. There's kind of a caveat to this. I'm not going to worry about it right now. So squaring doubles all exponents. Taking the square root halves all exponents. But that's not completely true. I'm not exactly lying to you, but I'm leaving out one thing that we'll worry about later. And so what are these square roots? Just make sure we see this. I'm gonna do square root of x to the eighth. Okay. And that's the square root of a string of 8 x's multiplied. Now, can I group these into 2 equal groups? I put 2 sets of parentheses on them, so each one has the same number of x's in it. So we can break this into 4 x's in a string of 4 x's. Okay. Each of these has half as many x's as we started with, right? Well, we say here taking the square root halves all the exponents. Okay, so half as many x's is just this, and that's x to the 4th. So the square root of x to the 8th is x to the 4th. Check by squaring x to the 4th. If x to the 4th squared equals x to the 8th, then x to the 4th is the square root of x to the 8th. Well, that checks out because x to the 4th squared is x to 2 times 4. And that's x to the 8th. And check mark there. Now, can you do the same thing for the square root of x to the 12th? Okay, now, we won't ordinarily write all these out. For example, you get down to this one, you have to write 38 y's. You get down to this one, you have to write 82 x's, 64 y's, and 96 z's. We're not going to do that. But let's see what the pattern is here. As we did up here, I broke this into 2 groups because I'm taking the square root. And why did that work? It worked because one of those groups squared gives me twice as many x's, which is what we want. Okay, well, I group 1, 2, 3, 4, 5, 6 of these, and it leaves me 1, 2, 3, 4, 5, 6. So this is equal to one of these groups. If this times this equals x to the 12th, then the square root of x to the 12th is going to be half that group, okay? Half the big group. And we check. If we square x to the 6th, we get x to the 2 times 6, or x to the 12th. So there we have it. Now, to do this one, what I'm going to say is this is half. What's half of 12? You can show me with your fingers if you know it off the top of your head. Is that 6 or 7? Okay. Okay, so what we notice here is we've cut this string of 12 things into 2 equal strings, which means we've got half of it. Okay? So the answer is half of as many x's as we have here. That's what I mean by taking the square halves all the exponents. Okay? By halves, I mean that's in half. Okay? So here we've cut in half all the string of x's. Here we've cut it in half. So we're going to cut it in half here. Actually, I'm going to do this one because I don't really have room to do this one. I'll squeeze it in. I'll write this one a little bit lower. Let's go to this one. So I'm going to say this equals x to the 82 divided by 2 times y to the 64 divided by 2 divided by z to the 96 divided by 2. That way, without having to write them all out, we can cut that string of 82 x's in half. And then we can figure out how many there are. We cut the string of 64 y's in half. We can cut the string of 96 z's in half. So what do we get? Okay, so 82 divided by 2 is 41, so we get x of 41. 64 divided by 2 is 32, so we have y to the 32. 96 divided by 2 is 48, so we get z 48. Now that's pretty easy. But you don't want to lose track of why you're dividing these by 2. You want to be sure you see this. But you don't want to have to write out 82 x's and figure out how many to group to cut it in half, right? And then we can check. If we square this, we get x to the 2 times 41 times, that's not x, y, times y to the 2 times 32. And that'll be divided by z to the 2 times 48, which is x the 82 divided by 64 over z to the 96. Okay, it has to work if you cut all these powers in half. All right, if we want to do the square root of x to the 7th, we could divide 7 by 2 and we get 3.5. So we get x to the 3.5. That's valid, but the most simplified way of writing that, well, this is what we really want to do. You write the square root of okay. 1, 2, 3, 4, 5, 6, 7 of them. Now we can't divide this exactly in half. Okay. If we tried to do parentheses, we'd have to put one set of parentheses that cuts this x in half, and the other set of parentheses that have the other half of it. And that's, yeah, that kind of corresponds to a 3.5 power. You'd have 3.5 X's in each one, but it's half X. Okay, so what we do is we divide this into the two biggest equal groups we can. And I'll say with as little as possible. Left over. Okay, well, let's see what we could do. I'm just gonna kind of do this off to the side in different color, so we don't confuse it with our actual solution. What I've got. There's 7 of them, okay? Now, what could I do? What equal groups could I use? Well, I could use equal groups of 2. Okay? What would I have left over? I'd have 3 X's left over, right? Okay. Well, I've divided it into equal groups, but is there a way to do 2 bigger equal groups? So can we write this out? And make 2 bigger groups, equal groups, that have left over. Right here, a group of 2. Leave X times X times X at the end. Okay. So if we wanted to do a bigger group, what number could we use? Okay, you look pretty well here. To clarify, I got the question from one student, do they have to match each other? Yeah, because that's what we mean by equal groups. They match each other, they have the same number of X's, okay? So as soon as we got that, what equal groups means clarified, we immediately got this. Because we tried groups of 3. If groups of 2 doesn't work, we're going to try groups of 3. Assuming there's still something left over, okay? This group works, leaving a single X. And we can't do groups of 4 because that would require 8 X's, right? Don't have 8 X's, we only got 7. And to do 2 groups of 4, only 4 makes 8. Okay. So we can now say that this equals this. Okay, well, that equals, and it turns out we can always break a square root of product of a bunch of things that are multiplied. We can group them any way we want and write this as two square roots. This would be the square root of x times x times x, multiplied by x times x times x, and then we multiply that by the square root of x. I still got 7 x's under the square root. I would only do this if they're multiplied. And the square root of this is just plain old x times x times x. Square root of this times this is just this. Which is x cubed times the square root of x. Okay. Now, so we're saying that the square root of x to the 7th is x cubed times the square root of x. Let's check that. X cubed times the square root of x, quantity squared is x cubed squared times the square root of x squared. Well, x cubed squared is x to the 2 times 3. And the square root of x is the number you square to get x. The square root of x squared has to be x. Assuming x is positive, we'll worry about that later. So x to the 2 times 3, well, that's x to the 6. X is just x to the 1. We can write this as x to the 6 plus 1, which is x to the 7. That checks because it matches what we were taking the square root of. So by this whole process, we see square root of x to the 7th is x cubed times the square root of x. And we check that. See that if we square this, we get x to the 7th. So the square root of x to the 7th is x cubed square root of x, because if we square x cubed square root of x, we get x to the 7th. Okay, let's do the square root of 96. To do that, we can always do a prime factorization. Well, 96. If you divide 96 by 2, you get 48. If you divide 48 by 2, you get 24. So 48 is 2 times 24. Now I've done a bunch more steps. I'm not going to explain every one, but what we've done is we've divided every number we get by 2. We divide 96 by 2 and we get 48. Then we divide 48 by 2 and we get 24. And we write down the 2 and the 24 because 48 equals 2 times 24. Okay, then we divide 24 by 2 and we get 12. So 2 times 12 is 24. We divide 12 by 2 and we get 6. So we know that 2 times 6 is 12. We divide 6 by 2 and we get 3. Knowing then that 2 times 3 is 6. So that 96 is 2 times 2 times 2 times 2 times 2 times 3. So this is the square root of 2 times 2 times 2 times 2 times 3. We can write this product, the square root of this product, as square root of this part of the product times the square root of this part of the product. Now, why in the world would I do that? Well, I do that because now I can group this product this way. And the square root of this is just 2 times 2. 2 times 3 is 6. This is the square root of 6. So this is 4 times square root of 6. I'm going to do another one. I'm going to write it up and see if you can do similar to what I did. Well, first let me show you the rule. A shorter version is the square root of 96 equals. No, I'm not going to show you that one. Let's stick with what we've got for a moment. You're going to have to pick up some of this from the open math homework. I'll give you some rules and some examples that you can follow, and I'll come back to this. Okay, so let's do the square root of 2 to the 7th times 5 to the 30th. Okay. Now I can write all this out the way I did. No. I forget what I just started to do. We're going to continue with this. Idea that wasn't the best idea I've had on this. Okay. To shortcut all this writing, we can say that the square root of 96 is the square root of 2 to the 5th times 3. Now, what power of 2? Well, yeah. Okay, try. What I'm doing here is evolve out of what I see in class and put it together in the best possible way. Okay. I'm just going to say that this can be written as a square root of 2 to the 4th times 2 to the 1st times 3. Why did I do that? is because I don't want an odd power of 2 because I can't cut it in half. I can take half of 5, I get 2.5, but it doesn't give me a whole number. Okay? I can take half of 4 and I get 2. All right. So what I do is I split this into the biggest even powers I can, and then whatever's left over. The biggest even power I can use on 2 is 2 to the 4th. Well, the biggest even power I have within 2 to the 5th is 2 to the 4th, just like I have here. Then I can write this as the square root of 2 to the 4th times the square root of 2 to the 1st times 3. And what's the square root of 2 to the 4th? You take half the power. So the power becomes half of 4, which is of course 2. And we get 4 times square root of 2 times 3, or 4 times square root of 6. And now there's actually more steps here than there were here, but there's less writing out of the 2 in this case. And of course, we had a high power of 2. We need to use the rule here. Okay. So again, the idea is we take the biggest even power of 2, and then whatever's left over. And then if 3 has a power greater than 1, we do the same thing for 3. This works because this is what it all is. But let's try this square root of square root of 5 to the 6 times 7 to the 9th. Now, what did I do to 2 to the 5th? I wrote it as a product of the highest even power of 2 that I could have, then just times 2. Okay, what's the highest even power of 7 that you have from 7 to the 9th? Okay, so if we did a prime factorization of some number, and I can't calculate it in my head, okay? Yeah, 5 to the 6th I can probably do, but 7 to the 9th, don't even want to attempt it. Okay. Okay, we want to use the biggest even power of 7 that's less than the power we have. We have 7 to the 9th, which is 7 to an odd power. So the even power, biggest even power less than that is just 1 less than 9, that's 8. So we have 7 to the 8th. And of course, we still have 7 to the 1. So we can write this as 5 to the 6th times 7 to the 8th times 7 to the 1. We can put the 5 to the 6th and the 7 to the 8th into one square root, and the leftover 7 into the other. And we get remember, when we take the square root, we cut the power in half. The reason we want to use just even powers is an odd power doesn't give us a whole number when we cut it in half. even powers do. So we do 5 to the 6 over 2. Seven to the 8 over 2. And then we still have the square root of 7. Giving us 5 to the 3rd. Times 8 to the 4th. Times the square root of 7. Now 5 to the 3rd is 125. 8 to the 4th is 4,096. Whatever 125 times 4,096 is, that's the number we have out in front, but then we'd have times the square root of 7. Okay? And of course, you can do that with a calculator. What you can't do with a calculator is just plug in square root of 5 to the 6 times 7 to the 9th and get something that makes sense. It's not going to reduce it for you in lowest terms. At least a basic calculator won't do that. Okay? You got a symbolic calculator, it will, but we don't want to use symbolic calculators for things that we can do. Okay? At least not right now, till we learn to do. Okay.